got to yesterday, right? This is how far we got yesterday, correct?
Yeah.
And before we put these radicals on top, before we put these guys on top, let's focus on this one. What did we call this, Eric? Do you remember what name we gave that? It starts with a V. Who remembers? Put up your hand. VA, yes, Alexa?
Variance.
Yeah, they called that variance. Okay. And they developed this. Again, notice we're eliminating the problem by squaring individual deviations where we're taking any negative deviations and they're making them positive, so you don't have the offset that you did with the sum of just the straight deviations as we showed equals 0. So that takes care of that. We're not dealing with abs-val, which doesn't present problems with regards to calculus and continuity. We're averaging the sum of the squares of the deviations. And no, not yet, my friend. And then we're saying, okay, well, we'll call that variance. And you have that in your notes from yesterday, right? I gave you that in your notes. Recognizing that variance is effectively a square of the units of the one variable statistic that you're dealing with. If you want to express things in the same units, you can take the root of that. So if x was your unit and it was in centimeters, obviously variance would be centimeters squared. Well, if you take the root of that, you get centimeters. So variance and standard deviation are effectively the same thing, right? One is the square of the other. Lowercase sigma is going to be the defined symbol for standard deviation. And for population, this is the formula. And you look at this and say, well, if they're going to be mathematically the same, you would simply write that. You convert your uppercase n into lowercase n, keeping in mind that if this is n, this is the universe of, sorry, this is the entire population, that lowercase n is a sample of that population, a random sample. And this is not good. What should this be right here?
X bar.
Yeah, it needs to be x bar. So these have different symbols, but they mean the same thing. They both mean average. One means average of the entire population, one means average of the sample. And again, lowercase n is a sample of the entire population, but then you see this deviation. You see this mathematical deviation between the two. And this is the first mathematical deviation between population and sample of population formulas, aside from just the aesthetics in terms of the character differentiation that we use, say x bar and u. And so then the question became, well, why did they being statisticians, and I'm not sure, I can't remember the name of the statistician that introduced this first, but what's a good reason for that? What's a good reason for incorporating that negative one in that denominator? Yeah.
It cannot be 1, like it has to be more than 1. And
okay, so you're saying if you take one data point, okay, but then why not just leave it like this? Yeah.
Because I think S is just a sample of the whole group, so it is just
S. I mean S.
That one.
S is just doesn't stand for sample. It stands for well, it stands for standard deviation, but we mean for sample of the population.
So it is just a sample of the population. So it is just.
What is it? When you say it is just a sample of the population, what do you mean by it? What's it? Hang on.
What's it?
Yeah, when you said you started a sentence, you said it is just a sample of the population. I don't know what you're talking about.
I mean this standard deviation is for the sample of the population.
Yes.
Yes. So the sample of the population is not exactly as the whole population. So it is just an approximate. So you minus 1 in order to get closer to the.
Keep talking.
Get closer to the standard deviation of the real population.
Okay, excellent. So that's he just took half of the way there. It took you half of the way there. Of course, whenever we have information for a sample, ideally we want, ideally we'd like to just do this, right? We don't want to do sampling of populations. We want to get information on the entire population, but reality dictates that we might not be able to do that all the time, right? And so Ken is absolutely correct in saying that there's got that -1 over there is basically saying, well, if you don't have the -1, then the standard deviation that you get of your sample is not necessarily representative of the standard deviation for the entire population. So this is going to somehow offset that imbalance to an extent and make this really more representative of this. And my question is why? So that's good. Yeah.
I think it's because like entire populations tend to deviate more because there are just more values there, while a sample tends to deviate less because you have less values that could deviate.
Yeah, now we're getting there. I would be even more specific than that. I would say something like this. I haven't shown you a probability graph yet, so well, I guess you know histograms. Let's say you're dealing with a population of I don't know, 1,000, let's say we're talking about heights of folks. You will have a few people at the top end that are incredibly tall, ridiculously tall, right? And you will have a few people at the bottom end that are ridiculously short, right? Now, if you imagine those people in the sandbox, you go in, you're God, and you go in and you grab randomly, 30 people, right? Presumably, if you're grabbing information, or if you're grabbing people randomly, then the proportional makeup of what you have should be the same as the entire sample. So let's say there were 100, and let's say there was one really, really tall person and one really, really, really short person. Okay? And you go in and you grab 10 people. Are you necessarily going to grab the one tall and the one short? You might miss them entirely, right? I mean, mathematically, it would be a scale. It would be, maybe you'd have like, a percentage of the short and a percentage of the one tall, like his arm.
They don't affect much like the population.
Sorry?
They don't affect the population that much with their heights because there are only 2 people.
Oh, but they do. You see, they affect this number very, very large, particularly because of the fact that this is a square of the deviation. So if your average is here, and you have the really, really short person and the really, really tall person in your calculation, see, people that are close to the average, this distance squared is not that big. But this distance squared is huge, and this distance squared is huge. So in fact, outliers have a huge
impact.
Quantity contribution to standard deviation or variance. And you can see that because it's the square, right? It's the square of the distance, right? Not to mention the fact that even without the square of the distance, it's just a bigger distance, right? Now you're squaring that big distance, it's massive. But when you go into a sample, when you go into a population route and you grab a sample, all things being equal, even though you're still going to grab things proportionally, even though your sample may be a perfect proportional representation of reality, since there were so few of those outliers to begin with, you may be missing them altogether in your sample. You guys understand that? No? You don't get that? Who does get that? Nobody. 1, 2. Who does not get that? One person. So
The rest is
you don't follow? Here we go. I don't know. Let's say we have. I'm going to end up repeating myself, but. Here, 100 people. Right? And let's say we're talking about heights. Okay, and let's say this is going to be percentage of population, and this is going to be height. It could be in centimeters, it doesn't matter. Let's say this is average height. Let's say this is going to be the average height. Let's say it happens to go like this. Not saying that every population looks like that, but do you guys understand what I mean by that graph? So I made a symmetrical graph here. We'll talk about that in a continuous manner. We'll call it a normal distribution later, but that doesn't matter. Let's say this is the average height. You see that most people in this world that I created tend to, the greatest, if you look at the population density as a function of height, you see that you have the greatest proportion of people at that height, right? And then as you deviate from that average, it starts to fall off, right? You have very, very few people that are super tall and very, very few people that are super short, right? Let's say there's one person here that's super short. And let's say there's one person here that's super tall. Now, if you were to go ahead and figure out what the average height is, right? Add up all of the heights, divide by the number of data points, which is 100 here, right? That would give you mu. And then you would go ahead and you would figure out the deviation and square it for each one. So this person, I don't know, might be 3 foot 4. Okay, very short, right? You go 3 foot 4, well, in centimeters, I don't know. Take away the average height of all these people, square that and add that, this person's height less the average height squared, and so on and so forth. How many of you guys see that mathematically these two data points are going to have the greatest impact on the size of this number? See that? Of course, right? They're the furthest from the average, and then that gets squared too. It's just they have the biggest contribution. Now, let's go to here. Let's say you can't grab 100 people. Let's say you can only grab 10 people. Is it reasonable for me to say that there is a chance, a good chance, that I may not grab these people?
Yeah. You just grab the top.
I might only end up grabbing, because there's so few of them, right? It's like if you have a sea of marbles, right, of different colors, and like a lot of blue marbles, and let's say, you know, like less red ones and a few purple ones, but like there's one yellow one and one green one. And you go into the 100 marbles and you take 10, it's conceivable that you may miss the green and the yellow marble.
Yep.
Well, what that means is when you go ahead to do that calculation, even though the average might be the same, let's say you missed both. Let's say you missed the green marble and the yellow marble. You're still going to have balance that way, right? So your average may still stay the same. Agreed? But in terms of spread, things just got a lot tighter. Agreed? Now it doesn't look like it on this graph because I just got rid of these two little tick marks, but mathematically, look what that means. It means that this data point and this data point are not involved in this calculation. And you just told me that those two data, you agreed with me rather, that those two data points are going to be the data points that give by far the biggest quantitative contribution to this value, right? Which is going to be positive. There's not going to be any negative stuff because this is squared, right? So like if you think of this as being that, where the height of that, it represents the quantity of that particular thing, well, if you did it for the entire population, you would get this. Well, if you miss those two data points, maybe you chop off this much. This is going to drop down, right? And as Ken pointed out, the idea of doing a sample is always to get an idea of or a reflection of a representation, thank you, of what's really going on with the entire population. So you might say, well, this is the spread of the data about the average for that population. Then you may go ahead and make decisions based on that. But in reality, it's really that tall because you missed those two because your sample was small. right? It's just a reality because there's always a reasonable probability you're going to miss outliers if those outliers exist, since those outliers exist in small quantity. Okay. So what does that -1 do? It inflates the value because obviously you decrease your denominator, right? You decrease the size of your denominator, you increase the size of the entire value. So it artificially inflates, it artificially reinflates the sample standard deviation to make it start to approximate that reality. And of course what's cool about it is the limit of n minus 1 as n goes to infinity. When n sorry, I shouldn't say infinity. As n starts to, I can't say this because it's not going to infinity. But what I can say is that as n approaches capital N, I can say that the significance of this -1 becomes, as n starts to approach this value of n, does that -1 have a greater or lesser effect? Lesser and lesser effect, right? So let's say you weren't dealing with 100. Let's say you were dealing with a sample of 10,000. Well, sorry, a population of 10,000. Well, if you only did a sample of 10, right? If you only sampled 10 of those 10,000, then you'd have a 10 minus 1, which is 9. That's a 10% decrease in your denominator, right? If you originally had a value of 10 here, but instead you did this -1 thing, you've gone from 10 to 9. That's a 10% drop. That's a measurable increase in your denominator, which is going to artificially inflate the overall value significantly, which would make sense because if you're only grabbing 10 out of 10,000, there's a really good chance you're missing some of those outliers, right? But if you sampled 9,000 of those 10,000, well, now you're dropping from 9,000 to 8,999. Is there a big difference there?
Yeah.
No, there's not a big difference between 9,000 and 8,999, nor should there be, because when you're at a sample size of 9,000, you're pretty close, you're a hell of a lot closer to the total population size, and you're also much more likely to have grabbed, if not all of those outliers, if not all of these outliers, at least some of them. So you don't need as much of a compensation, if you will. Okay? So, yeah, I think that's all I have to say about that. I know Milad was going to say something, but before he does, are there any questions on that? Is that better? Is that a little clearer now? Yes?
Why is the square root incorporating the denominator? Why is it to divide it after?
That's an excellent question. I'm not sure. And if you ask me, if you didn't incorporate the denominator, then the difference would be between having a denominator of, let's say, that, or having a denominator of that, right? So that's basically 2 over 2. So it's almost like you're adding in a factor of -1/2.
There's actually a pretty noticeable difference between just square rooting the numerator and the divider.
Oh, there would be a difference. Now, in terms of the value of the result, I'm not sure. I don't think there would be a difference in terms of value because everything would be still relative. So you'd be dealing with a constant. It would be the difference between a constant, right? Because in this case, you can think of that as root of numerator over root of denom, right? Versus just having root of numerator over denom, right? So the difference between these two is a constant, right? Which you could have imagined as being pulled out. So if you kept that consistent across the board, right, it wouldn't make any relative difference. Now, you're absolutely right. It does make an absolute difference. I don't know why they would have defined things that way. Maybe that's something that you guys can figure out. I don't think it would make any relative difference in terms of making decisions on the.
No, because yeah, values that are greater will still be great.
Right.
It doesn't make it.
Oh, quantitatively, it'll make a difference for sure. Well, just like you know, this will be standard deviation. If you get rid of that, they didn't give variance another letter, they just call variance the square of that, so that would be variance, right? And of course, that numerically is a hell of a lot bigger than that. And sometimes you see variance quoted instead of standard deviation, vice versa. Okay, Milad.
Why is it exactly -1?
That's an excellent question. Why not -5?
Not -2.
Why not -2? Can't answer that. I do not know. That's something for you guys to
And
investigate.
sometimes that -1 makes it even worse. If you only grab the outliers by those 10 and don't grab the middle ones,
And
that
that-
-1 makes it way worse.
And that's why if you take a look at, and that's why when you take a look at statistics, right? There's always uncertainty associated with statistics. There's always uncertainty. Nobody can give you a guarantee of anything. If you take a look at any of these snapshot polls that are going on in the United States right now with the election, you know, Obama 49, Romney 45 in Virginia, there's going to be a plus minus associated with that. Okay?
I know,
Sure,
but
the-
there should be a logic for that -1.
Oh, the actual quantity is a 1 as opposed to a 5 or a 4? I'm sure there's a logic. That I do not know. Or I'm not sure. There may be a logic to it. I cannot tell you. You'll have to check it out. Why it's 1 and not 50, I don't know. But the effect of it, I know. And that's what I've explained to you. One aspect of this course, which used to be part of the curriculum, which is gone, has to do with things called confidence intervals and so on and so forth, and the mathematics associated with how you can quantify the degree of uncertainty associated with statistics that you calculate. Because of course, if one person conducts a survey for me and says that there's a plus minus error of 5% associated with it, and another person conducts a survey and says there's an error associated with it of plus or minus 2, obviously I want the survey, if I want that information, I want to go with the plus minus 2% survey. We're not going to get to look at it in this course, unfortunately. Well, we may, if there's extra time and you want to, we can do it. Otherwise, those of you continue with stats, we'll look at it in university. But I mean, yes, there's always the probability, Milad, that you grab a sample of 10, and yes, in that sample of 10, you grab the yellow marble and the green marble, in which case you would really be throwing off your information because you would end up with a standard deviation that's way too high, right? Way too high. Because in actual fact, if you only grab 10 marbles and you grab the tallest and the shortest person, well, as it stands, that's artificially going to inflate it because 20% of your data does not include the tallest and the shortest person, only 2 out of 10,000. And then you're going to further artificially inflate that value by taking away 1 from the denominator. And that's a chance that you take. Okay? But another thing I suppose that you could do is you could do multiple trials. And you could average the standard deviations, couldn't you? But a smarter thing to do would simply to just be, I think, take a larger size sample size. Because if you're going to do multiple trials, that means you've got to go in again anyways and get a random sample. So why not just take the biggest sample you can take? Anyhow. All right, so that takes care of that one. I think we're almost done with 2.6. I'm going to finish with it today, and then Eric had a question, and we're not going to do much more. We have short periods here, right?
Yeah, very short. 45 minutes.
Okay, so there's box and whisker in here. Actually, this kind of ties into something that I just said. If you take a look at page 140, I don't need to write this on the board. You can see standard deviation and sample of standard deviation formula approximations for group data. Remember how we did formula approximations for averages of group data? Remember that's when you have the stuff in bars and you have 5 folks in a bar from 0 to 10 or something, but you don't know the breakdown within the bar. So we just assume that all the people in the bar are at the average and then we multiply by the frequency of the bar. So you have approximation formulas there for group data. And then you go to page 141 and you get this thing called box and whisker plot. And it's very, very easy. It's it's free marks for you guys to get, so we'll go over how to draw one. The practical application for it, as I see it, which isn't covered so much in this course, well, which isn't covered in this course, but I can at least show it to you, is let's say you were dealing with a two-variable statistic of, let's say, y versus x, and let's say you had a bunch of data points. The reality is that in many statistical, the reality is that in a lot of research, these data points sometimes are very difficult to arrive at, and sometimes those data points are kind of an aggregate of a lot of information. Sometimes there's actually uncertainty associated with the data points, or spread associated with getting a data point. And if you're a researcher and you're presenting this information to folks, and perhaps those folks are also, they have an awareness of statistics, perhaps their colleagues and so on and so forth, a lot of those people have an expectation that you can present to them the variation associated with each of those data points. And so sometimes you'll actually see those data points reflected as box and whisker plots. And so on, etc. So that way you have the data. This is a data point. This is a data point. This is a data point, but it tells a macro and a micro picture. It also gives the user or the reader an idea as to the uncertainty associated within the overall trend, which can be very important. And you take a look at a lot of research papers, statistical information that's published. A lot of it, which has, a lot of gravitas, if you will, associated with it. Papers on the effectiveness of drugs, that can affect the outcome, the survival rate, or rather, that can affect whether or not people survive. And you'd be shocked to find that there isn't always so much data on these drugs, right? Either A, because these drugs are new to the market, or B, perhaps they have a high stakes effect on people. Maybe they're very, very intense drugs. You don't necessarily have a million people that are willing to jump in to those surveys to try those drugs. Or, for example, the trial might be predicated on the fact that the people involved are people who are sick. And if the disease is niche, then you might not have that many folks who have that niche disease. As a result, you don't have that big of a population to begin with. So you might not have that much data. So box and whisker plot is a way of actually showing the spread associated with data. And it's pretty straightforward. It's based on the idea of taking the range of your data and breaking it up into quarters, or 4 parts. So, for example, of course, we're not going to do all of this. We'll just focus on, let's say, we're doing one data point. So let's say you had, we'll keep it simple. So box and whisker plots. So let's talk about a scenario here, or we'll just call it question. Design box and a whisker, and there's another type of plot called a modified B and W plots for the following data. So I'm going to list, let's say these are percentage, let's say you had a quiz or something. Let's say you had a quiz, and let's say it was out of 10 marks, okay? I'm going to write down the marks of everybody in the class, okay? So, one person got an 8, you got a 9, you got an 8, 10, 10, 4, 3, 5, 5. So 7, 7, 7. Maybe there was another 8, 6. Just out of it. You want a 0 in there?
What about the extra one?
You want a 0?
11.
We'll give it a 0.5. Just for writing their name.
What?
Somebody, they wrote their name, we gave them half a mark. Okay, so now what we want to do is we want to design a box and whisker plot to present this information, right? So the first thing that we want to do is we want to rewrite the data in ascending order from lowest to highest. Somebody want to call out that information?
No.
0.5 is the lowest. What's next?
4, 3, 3, 3, 4.
How many 4s?
1, 2, 5, 6, 3, 7, 3, 8, 1, 9, 2, 10.
Okay, we gotta be careful because I gotta remember how this works. So, I want to double check the number of data points. You guys are gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 5 by 3 is 15. So that checks out. You guys have given me the right number of data points. So now, what we have to do, and I always forget this part, and we'll double check the book. The first thing that we want to do, so we want to end up breaking this stuff into quarters. So what we first do is we take all of the data and we find the median, we break it down the middle, and then we have 2 halves, right? And then we take each of those halves and we break each of those halves in half. Now, the one thing we should check the book for, I can't remember, is do we just put a line right? Well, first of all, we have to check to see whether or not we have
7 is the median.
we have to check to see how many data points we have, right? Because we have 15 data points.
So there is a
So in this case we have an odd number, right? If we had an even number, we'd have to treat it a little differently. So if we have an odd number of data points, middle data point is the 8th, correct? Does that make sense? The middle data point is going to be the 8th, which is basically taking all of the data and breaking it in half, right? And then rounding up to the middle. So if this is 1, 2, 3, 4, 5, 6, 7,
8.
8, 9, 10, 11, and so on and so on. So,
you count 0.5 as 2 numbers.
oh, sorry. So first, second, third, fourth,
8.
and that's our 8 right there. So what I want us to check on the book, in the book, is if we break this right down the middle here, and if we push that 7 there and that 7 there, or if, since they are the same number, we just clump them all up. Do you know what I mean? I feel like we're going to throw one to the left and one to the right, but I'm not sure. So let's take a look at the book and see that. Do you know what I'm asking?
Yeah.
I'm not sure if we just bunch the 7s as a group and say, well, they're all the same, and then just, I don't think so though. I'm not sure. Let's read. What does it say? You guys take a look. So while you guys do that, I'm going to call this the median, right? And then while you read, then you guys will figure it out and tell me. Kate is here, German is here, Rohan, are you here? Ilya, are you here? Anthony, are you here?
Here.
Micah, oh shoot, let her in.
Class is
We have 5 minutes soon.
I forgot.
Let's say, oh shoot.
Arthur, no, he's not here, right? He's never here. Aaron is here. Eric is here. Michael. Wally is not here. No, not late. Nikita. Janice and Yanjun are here. Jamie is here. Tony is here. Krish, not here, right? Brijesh is here. Preet is here. Juan is here. Milad is here. Darwin is here. Aaron? Is Aaron here? Alexei is here. Naomi is here. Kevin is here. Okay, what did you guys come up with? Huh? Sorry?
Did you call my name?
Yeah. I marked you here. Sorry, Micah. So what do you got? Does it have an answer?
The book used even amounts, so yeah, we don't know.
It says what?
The book used even amounts of
They
data.
what use even amount? What?
They use
The book.
even amount.
The book used even amount.
amounts of data points, so it's just split down the middle.
Okay, so you are saying, I didn't fully get it, you're saying throw a 7 on the left and throw a 7 on the right.
No, like you have odd amounts of data points, right?
Okay, but the book doesn't have a more general, you're just looking at an example?
Yeah. they
Okay, but
don't.
what about the words? Yeah.
So you don't need to throw that 7 anywhere. 7 is the middle point. Why would you need to throw it anywhere?
He means the two.
You're not gonna say like say the quantity here, like it's just gonna be like your line on 7.
So when we go ahead and we get, because we've got, I guess what I'm saying is, the reason why I'm asking is because now, let's say I went to the left side, right? Maybe I'm wrong, but when I go to the left side, I have to now find the median of the data on the left, right? So I have to find the halfway point of the stuff on the left and the halfway point of the stuff on the right. If I include the 7 on the left, then that affects where the middle value is on the left. But if I just use that, I get a different value. You see what I mean?
You're talking about those 3 7s.
I'm talking about the 2 actually on the edges. Do you see what I'm saying? You see, if I throw this 7 out, and if I just say, oh, this is just one value, then, hello. If I just throw this out, then I'm going to be finding the middle of that information, right? But if I leave that 7 over there, I'll be finding the middle of that information, which is different.
So the problem is in the book, it's not like that. The numbers are different, so it never talks about it.
Okay, but it doesn't. Okay, so how much time do we have left?
Nothing.
Are we done? Okay, so then what we'll do is we'll pick this up.
Sure, you see that. What if we throw 7 to both?
Well, I understand. We've got, but if we have to decide. I always forget. So we'll pick this up again next class. I'm saying, German, that's one option or another option.
I didn't hear.
I would.